Imagine materials that fix themselves, like a robot skin healing a cut.
Or hands so incredibly light, yet precise enough to handle, well, almost anything.
Yeah, these aren't just sci-fi ideas anymore. We're seeing breakthroughs in robotics that are really changing what robots can be and do.
Definitely.
Welcome to this deep dive. We're looking into some research highlighting two, well, pretty fascinating advancements. One's about making robots tougher, more resilient.
And the other is about giving them this amazing dexterity, this manipulative skill.
Right. So our mission, really, is to unpack these sources, pull out the key ideas, and think about what this means for, the future you'll be interacting with.
And what's striking from these sources is this move away from robots as just rigid machines.
Yeah.
There's this turn towards biology, finding inspiration there to make things that are both tough and delicate. It's quite a shift.
Okay, let's dig into that first one, the one that really jumped out at me from the research, this robot skin or maybe muscle that can actually heal itself.
Yes, the work from the University of Nebraska-Lincoln. Eric Markvicka's team.
That's the one.
The core idea is pretty cool. Build soft robotic parts that can genuinely repair themselves when they get damaged. A bit like how our own skin heals.
Building resilience right in. So how do they actually do it?
Yep.
The sources mention a layered structure.
Exactly. It's essentially 3 layers working together. Each one has a specific job.
Okay, so the bottom layer, what's its function?
That's the sensory part. It's silicone, but it's got these tiny droplets of liquid metal inside.
Liquid metal.
Yeah, it forms a conductive network. So its job is basically to detect where damage happens, like sensing a break in a circuit.
Got it. So it feels the cut. What about the middle layer? That's the healing part.
That's where the magic happens, yeah. It's a thermoplastic elastomer, so it's rigid normally, but it melts when heated.
Okay.
That allows it to flow into any damaged spot and seal it up.
And the top layer?
That's for actuation, making it move. It allows the whole structure to act like a soft muscle when you pressurize it, maybe with water, like the source mentioned.
So you've got sensing, healing, and movement all packed together.
Pretty much.
So how does the repair actually kick in? The bottom layer senses damage. Then what?
Well, when there's a crack, it creates a new electrical path through that liquid metal. The system monitors this using 5 different currents.
Okay.
By seeing how those currents change, it figures out exactly where the lesion is.
So it knows the location. How does it trigger the repair?
It sends current specifically down that new damage pathway. And that current generates heat, the Joule effect.
Joule effect. That's just resistance heating, right? Like kind of toaster coil.
Exactly that. Just very localized heat right at the damage site.
And that heat melts the middle layer.
Right. It melts the thermoplastic, which flows into the gap, seals the wound, and then solidifies as it cools. Structure restored.
Okay, this next bit from the sources really caught my eye. They use something called electromigration. Isn't that usually a bad thing in electronics?
It absolutely is. That's what makes this so clever. Electromigration is usually the enemy metal atoms moving around under current, causing circuits to fail over time.
Right, it degrades things.
But here, they turn it into an advantage. After the healing is done, they intentionally use electromigration in the repaired area.
Why?
To basically nudge the liquid metal atoms around just enough to erase the electrical scar of the damage from that bottom sensory layer.
Oh, so it resets the sensor.
Exactly. It wipes the memory of the injury, so the skin is ready to detect and heal new damage, even in the same spot. They repurposed a failure mechanism into a reset button. That's really innovative.
That is brilliant. So, thinking about where this could be used, the sources mention challenging environments, like agriculture.
For sure. Imagine robots in fields dealing with thorns, branches. Small tears are inevitable. A robot with this skin could just fix those minor damages itself. Less downtime, less maintenance. The sources definitely point to that kind of rugged use.
And any other applications mentioned?
Yeah, they also talk about wearable medical devices, making things like prosthetics or health monitors more durable for everyday life. Resisting bumps and scrapes.
Makes sense. And if things last longer, repair themselves? That ties into reducing e-waste, which the sources also noted.
Absolutely. Damage is a huge reason perfectly good electronics get thrown out. Self-healing extends lifespan, meaning less waste. It's a potential environmental positive, too.
So why does this matter to you, listening? Well, think about robots becoming more common homes, hospitals, public spaces. If they're more resilient, less likely to break from minor accidents, it changes the whole equation. Less need for expert repairs, longer usefulness, maybe less e-waste. It's a shift from replace to repair.
And moving from that resilience to how robots interact with the world, the sources also cover this really exceptional robot hand.
Ah, yes, the Kim research.
Yeah.
The hand that's lighter than an egg.
That's the one. Korea Institute of Machinery and Materials. What's remarkable is combining that ultra-lightweight with really high precision and stability in grasping.
How do they pull that off? Lightness and precision often seem like opposites.
It seems that way, but it's down to some clever mechanics. They use what's called a hybrid linkage-wire mechanism.
Okay, what does that mean?
It means they're combining the stability you get from rigid linkages with the fine control and lightness you get from using wires or cables.
So using both together.
Yeah, the sources say this lets the hand mimic a more natural human grasp. It can handle delicate things, but also grip firmly, adapting really well.
And the thumb control was highlighted as a big deal in the research.
It really is. They managed to get independent thumb movement using just one actuator, one motor.
Only one. How usually that takes multiple motors, right?
Right. They use something called the Geneva mechanism in a really smart way. It's a mechanism that turns continuous rotation into stop-start rotation. By applying it cleverly, that single motor can control the thumb's movement across two axes, letting it move much like a human thumb, but without all the extra motors and weight.
And using just one actuator must be key to getting that super low weight the sources keep mentioning.
Absolutely. Motors are heavy. Fewer motors mean a much lighter hand, down to that lighter than an egg level, without sacrificing complex function. That's a real engineering feat.
So where could this be used? The sources seemed focused on prosthetics.
That's a huge potential impact area, yes. For people using prosthetic hands, this could be genuinely life-changing.
How so?
The sources talk about enabling more natural, intuitive grasping, making complex gestures simpler to execute. Essentially, making the prosthetic feel and act more like a natural extension of the body.
Wow, that level of natural interaction would be amazing.
Definitely. But beyond prosthetics, they also mention humanoid robots.
Right.
Giving humanoids hands this precise and light makes them more capable. It reduces the complex calculations needed for manipulation and makes the robot quicker, more agile.
And the sources suggested this isn't just lab research. They mentioned patents, technology transfer.
Yeah, that points towards real commercial potential. They clearly believe in the mechanisms and are trying to get this technology out into the world. If successful, it could really boost the performance of things like myoelectric prosthetics.
So for you listening, think about what a hand like this could mean. Prosthetics offering near-natural dexterity. Or future robots, maybe in healthcare or delicate manufacturing, handling tasks with human-like skill.
And if you put these two breakthroughs together, the self-healing skin and this precise hand...
Yeah, what's the connection?
Well, you see progress on two vital fronts. One makes the robot physically robust, able to endure and maintain itself. The other refines its ability to interact, to manipulate things delicately and skillfully.
So they're not just separate cool inventions. They kind of point towards robots becoming, I don't know, more integrated, more biological in a way, robust and capable.
Exactly. More adaptable, more sophisticated in how they exist and operate in the world.
And as the sources hint, this obviously raises bigger questions, doesn't it?
It does. When robots can self-heal and manipulate with near-human skill, what roles do they take on? How autonomous do they become? How do we interact with them?
So, based purely on these sources, here's something to chew on. If robots can heal themselves and handle objects with such dexterity, what new possibilities or maybe what new challenges does that open up as they become part of our world?
A really interesting thought.
This has been a deep dive from the podcast to Philippe.
And if you found this useful, please do help us reach 1,000 subscribers. It lets us keep making these deep dives for you.
Thanks for joining us. See you next time.